This is problem 3-177E. It's on page 180. A section of pipe is supported by a saddle-like structure which in turn is supported on two steel pins as illustrated in figure P3-177. If the load on the saddle is 42,000 pounds, determine the required diameter and length of the pins. Use AISI 1040 cold drawn steel. Consider both shear and bearing. Alright, if you look at the picture, and I of course recommend you do, the pipe that's sitting on the saddle looks like this. The saddle is something like this coming down, and I haven't drawn it very well, but basically there's a pin through here and a pin through here. The structure is down here, and of course these pins are both loaded in double shear. Okay, so we don't know the length. We're supposed to size the length of these things, and we're supposed to size the diameter of them. Well, why would I say that? Well, the pins are loaded in shear here and here, of course, on both sides. And then if you consider the pin itself, or one of the pins itself, so you've got a shear load on either end, but also where there's contact between the saddle and the pin, you're going to have a bearing area. Okay, and that bearing area has to be designed to hold as well. Okay, so referencing the figure, the force on the saddle was given, in fact, let me just call this P for the sake of the video. The force on the saddle was given as 42,000 KSI, kips. So 42,000 pounds. And of course the AISI cold drawn, 1040 cold drawn, is something we can look up. If you do, you'll find it has a yield strength of 82 KSI. Since this is a ductile material, the yield strength is probably what's most important. Now, my solution strategy is to size the diameter of the pin based on the shearing stresses, and then size the length. Now, if the length ends up being excessive, what I'll do is go back and make the pin thicker. That'll give me more bearing surface area, and that'll decrease my length. Now, on the other hand, if the length ends up being very short, I can't really decrease the diameter because I need enough diameter to prevent the shearing. So we'll just start with the shearing and see what happens. Now, you'll notice that the load from the pipe, I assume, acts at the center of the pipe, and so I'm just going to assume that each pin has to take half the load. So basically, the load on each pin is going to be the total load over 2, and so that's 21 kips, or 21,000 pounds per pin. All right. Now, I'm also further going to assume that the load in this pipe is static. Maybe this is a pipe for the oil line that comes down from Alaska. I don't know. It doesn't matter. But we need a safety factor or design factor in order to get this started. So if you look in your book, you'll notice that the table for shear is toward the end of the chapter. Let me grab it quickly. Here it is, page 158. This is a static load, and so the design shear, page 158, static load design shear stress is a maximum of the yield stress over 4. So that's 82 KSI. I won't write all that down. 82,000 over 4 comes out to 20.5 KSI. So there's the maximum stress that I want to apply in shearing the pins. And so to calculate the shear in the pin, the shear is just force over area, but that's just the force on one single pin, because of course I'm going to design this for one pin, but divided by 2 areas. Why? Well, the pin is loaded in double shear, so I've got area over here and area over here to take the shear load. So if I solve for the area, it would be pi d squared over 4 equals the load on the pin over 2 times the stress. And so I can rearrange this to solve for the diameter. So basically this equation rearranged, the diameter is root 4 over pi, load on the pin divided by 2 times the shear. Now what shear should I use? Well, the 20.5 KSI is my design shear. So calculating the diameter of the pin is root 4 over pi. The load on one pin is 21,000 pound force over 2. The stress that we can allow in our design is 20,500 pounds force per square inch. And what happens? Well, pounds force go away, we'll get a diameter in inches. Factor comes out to about 0.807 inches. So I'm going to specify diameter equals 1 inch. That's my specification. Now, is it excessive? I don't know. I don't know what this goes into. I don't know if that's going to end up taking up too much space in this design. I don't have enough information to decide that. But if this is the closest standard size in decimal inches, now I could have gone to 7/8, the 7/8 pin, but what's the difference? Steel is relatively cheap, so I don't know if there's a weight constraint, but with that kind of load, I don't think the extra mass of a pin is going to make a whole lot of difference. So I'll just leave the specification at 1 inch. Now that should resist the shear. The next question is, what about the length? So basically, so far we've solved a shearing problem. Now let's solve the bearing problem. Okay. So basically now, how much length do we have to have enough surface area to take the load? Okay, well, the bearing area is recommended to be the projected area of the pin, which is the length times the diameter. And further, the bearing stress then would be the load on the pin divided by the bearing area. And so that would be the load on the pin divided by the length times diameter of the pin. And so the length required of the pin will be the load on the pin divided by basically the design or bearing stress multiplied by the diameter of the pin. Now the diameter of the pin and the load on it's already known. And we have to be careful here. We can't divide by 2 like we did before, because one pin just has one area for bearing. It doesn't have 2 areas like the shear did. So we can't have that nice factor of 2 in this. Now there is a recommendation. It's equation 322, and let's see, it's back a few pages. 322 is page 151. It says steel. According to AISC, see reference 2, the allowable bearing stress in steel for flat surfaces or on the projected area of pins and ring drilled or bored holes is, and it gives a number or an equation there. And that's what I've used. You may wonder, well, why wouldn't I use the equation below I used in a previous problem, 323, for rollers? Well, I've assumed that this is a static structure. There's no rotating motion or anything here. And so 322 looks like the more appropriate equation in this case, at least the way it's described. So they use the symbol sigma BD, but that's the same thing as what we've got. Anyway, they recommend using 90% of the yield strength. Well, 90% of the yield strength, that's just 90% of 82 KSI. That comes out to 73,800 PSI. So if I plug that into my equation here, then 21,000 pounds force on the pin divided by 73,800 PSI, which is pounds force per square inch, times 1 inch of diameter. Notice the pounds will go away. One of the inches will cancel. I'll be left with inches of length. That comes out to about 0.2846 inches. So this is a little over 1/4 of an inch. And so I just specified then that the required length of the pin be 0.3 inches long. Right? Wrong? I don't know. This is a design. It should work. It should resist the required bearing stress and the required shearing stresses. Is that a practical pin? That's a different question. So that should work, and we could go from there once we know more details about this particular application.